In this lecture, I'd like to support learning these materials. Design of analog CMOS integrated circuit by Razavi, and especially about chapter 16, page 662 and 663. And try explain example 16.5. I think it's need a little more further explanation needed here. And let's try to derive the solution of this transfer function when applied by step function. It would completed as 16.2, 21, and 22. So there's a transfer function from angular frequency omega input to omega output, which is like this. Or type 1 PLL. H of S equals omega n squared divided by s squared plus 2 zeta omega n sub n s plus omega sub n squared. And in page 662, the topic is applying this transfer function by applying 1 over s, which is unit step function. And times delta omega. And after that, example 16.3, applying some several hundred kilohertz, and requires stabilizing time before, just after the step to approaching 100 hertz to the final value. So we need to derive this inverse Laplace transformation as a function of t, which is omega output t. Omega out, omega in times delta omega is omega out. Omega in. This is like this. And this is S space and this is T space. A partial dividend is applied to express this h s over s. We need to expand like this as usual. Where S2 P1 P2 is solution of this equation. A マイナスゼータプラスマイナススクエアルートゼータスクエアマイナス1オールタイムドオメガやでピースオブ1イコールマイナスゼータプラススクエアルートゼータスクエアマイナス1オメガ n and piece of 2 equal to minus zeta minus square root of zeta squared minus 1 times omega sub n. And in these pages we deal the number zeta where zeta is positive but less than 1. In these cases, this time we treat this zeta only. So piece of 1 going to minus zeta plus j square root of 1 minus zeta square omega n minus zeta minus j times 1 minus zeta square omega n, where j square equal minus 1 imaginary number, and these are complex conjugate. And by the way, as usually we know the formula to derive k1, k sub 2, k sub 3. K sub 1 is such that h is over s times this s and applying s, the pole of s, 1 over s equals 0 origin, so this cancelled, and omega n, this is I assume this is factorized like this because of this. So these remain minus piece 1 minus piece 2, so this is omega n squared over p1 p2. p1 p2 is from some formula. We know p1 p2 equal omega n sub n squared, so this is just 1. So k1 is 1. The k2 is likewise, but this time s minus p1 applied and factorized, and s applied piece 1. So here remains s minus p2. So this is p1 minus p2 omega n squared. K2 likewise, K3 likewise, s minus p1 after applying multiplied by s minus p sub 2, we do this one, s equal to p sub 2, which is omega n squared over p sub 2 p sub 2 minus p sub 1, and p sub 1 p sub 2 equal these numbers, and the differential of these are this minus cancelled out zeta, and this is my plus minus minus my plus plus, which is 2j square root 1 minus zeta square omega sub n. So we have like this p1 zeta plus j. Good. Just I'll concentrating in calculation here, and this these are cancelled out. Expanding. J times j square equal minus 1. So this is this. And this is likewise, this is minus but this is, in this case, this is minus 2, p 2 minus p sub 1. And this squared is cancelled out, and this is minus plus plus, so these are 2j zeta expanding plus plus 2j zeta squared root 1 minus zeta 1, and minus minus plus 1 j square minus, which is minus minus 5, which is the same minus, then this is 1, and then hs over s is where if so sorry, just k1 equals 1 plus k2 e to the minus p sub t plus k sub 3 e to the minus plus p sub 2 t sorry, inverse Laplace transformation applied, and 1 over s equal unit function u t, and t where t is positive, non-negative number. Yes, this is 1, and this is like this. And e to the p1 t, e to the t2 t is factored out with e to the this minus zeta omega sub n, minus zeta omega sub n. P1 is imaginary number of j square root 1 minus zeta squared omega n, and the real number minus zeta omega n. And the real parts factoring out going to at this moment this is plus minus zeta omega sub n t k2 e to the minus imaginary part for p sub 1 j square root 1 minus zeta square omega nt for p sub 2 k sub 3 times e to the minus j square root 1 minus zeta square omega nt. And k2 k3 is this and this. We need to rationalize the denominator of these to factor out imaginary part and rational part, real number part, real part, imaginary part separation after rationalized version of K2 and K3 is applied. Only after that we can separate real and imaginary. So we need to do that. And then this is, we need to multiply both numerator and denominator by complex conjugate of these. In this case, 2j zeta square root 1 minus zeta square minus 2 times 1 minus zeta square. And here, minus 2j zeta square root 1 minus zeta square minus 2 times 1 minus zeta squared. It is then case of 2 equals 1 and 2j zeta square root 1 minus zeta square minus 2 1 minus square divided by this is minus 2 plus 2 minus 4 j square means 4. So 4 zeta square 1 minus zeta square plus 4 1 minus zeta square, and which is 4 zeta square the square 4 zeta square 1 minus zeta minus 8 zeta squared, so minus 4 zeta squared remain, and 4 zeta to the fourth, 4 zeta to the fourth minus plus cancelled out, remaining minus 2 times zeta square minus 8 zeta square remained. 8 zeta square 8 zeta no, this one plus minus 8 zeta squared so minus 4 this is just 4, and this is this, and 4 minus zeta square is the same for this case of 2 denominator, which is 4 times 1 minus zeta square, and the numerator is 2 times minus 2 times 1 minus zeta square minus j zeta square root 1 minus zeta square. And likewise, where k sub 2 equal 2 1 minus zeta square minus 1 minus zeta square minus j zeta square root 1 minus zeta squared. This is 1. And k sub 2 equal complex conjugate is minus 2 minus zeta square minus 2j zeta 1 minus zeta squared. The denominator is the same, and so 1 minus 2 1 minus zeta squared, and the numerator is minus minus 1 minus zeta squared, and this is minus j, so this is plus j zeta squared minus zeta squared. And the real number is this parts, and the complex part, imaginary part is this real number and imaginary parts. Multiply these imaginary number. So separate these. Because that we can write 2/2. This is 1 makes plus minus square root 1 minus zeta square. Zeta over square root 1 minus zeta square. Okay. Denominator and numerator multiplied by square root 1 minus zeta square, square root minus zeta, and this is cancelled, and this no remains, and this is minus. This is minus. This is plus 1, and this one. And there's a j. Of course, there's a j. And this, for case of 2, likewise minus half, and this is just 1. And this is plus. Likewise, 1 minus square root j. So real parts, separate the real parts. After separating real parts and factorizing minus half, we can get this one 1 plus 1 minus half. Just a moment. Minus half yields minus zeta omega nt times this one takes minus half, which means multiply this one. Just yield the j square root 1 minus zeta square omega nt plus yield the minus j square root 1 minus zeta squared omega nt, and then plus this imaginary part multiplied this imaginary part multiplied this and minus minus this is minus, so for this I need to make this minus j zeta over square 1 minus square minus this times this. Okay. And then in this case, case of 3, this one plus factorize minus 1, so this is minus e minus j square root 1 minus zeta square omega t is this is going to 1 minus e to the minus zeta omega nt. This 2 is coming here, and this makes cosine square root 1 minus zeta square omega nt. And this one, we need j for denominator, so minus j equal 1 over j. Okay, j square is minus 1. So this is plus zeta over square root 1 minus zeta square times 2j, this divided by 2j, which is sine square root 1 minus zeta square times omega nt. So we can derive this equation here. Then when cosine theta t theta plus a sine theta is given, we can use this transformation times just a moment. This is sine phi, sine phi. This is cosine phi. Okay, sine phi, cosine phi. The tangent phi equals this divided by this, which is 1 over a. And sine, cosine, cosine, sine makes this is just this going to be square root of a square plus 1. This is times sine theta plus phi. So we can simplify this like this: sine square root of 1 minus zeta square omega sub omega sub n t plus phi. But tangent phi, where tangent phi equals 1 over a. A is what is a? A is just this 1 over a. So 1 over a square root of 1 minus zeta square. And cosine phi is just 1 over a. Cosine phi is just a over square root of cosine 分の sine。cosine 分の sine、cosine ゼータ、ゼータ、cosine ゼータ。If phi going to half pi, this going to 0. This makes total oscillation. So, and zeta equal 1 where phi equals 0. If phi equals 0, zeta going to 1. And this is going to 0. And this is just 1. But the derivation assumes just this case. So zeta, when zeta equals 1 or zeta is larger than 1, we need to calculate another cases once again. But in this case, we can finally reach. We can finally reach this point, this solution. Then let's go to the next exercise. Example 16.5. Another I'll take with another recording.